Hey everybody, and welcome back to Differential Equations. Tonight we're going to talk about Euler equations. And we might remember that we just finished linear differential equations with constant coefficients. So at each term containing the derivative of y, or a derivative of y, the coefficient of that term is a constant times the nth derivative of y, a constant times the n minus first derivative of y, a constant times the second derivative of y, a constant times the first derivative of y, a constant times the 0th derivative of y, or y itself. Euler equations are also linear, but the coefficients of the derivatives of y are not linear. Here, the coefficient of the nth derivative of y is a monomial in x of degree n. And the coefficient of the n minus first derivative of y is a monomial of degree n minus 1. That's the pattern with an Euler equation. With an Euler equation of order n, the coefficient of the nth derivative is a monomial in x of degree n. The coefficient of the n minus first derivative of y is a monomial in x of degree n minus 1. The coefficient of the second derivative of y is a monomial in x of degree 2. And the coefficient of the first derivative of y is a monomial in x of degree 1. So the coefficient of each term in an Euler equation is a monomial in x. And the degree of the monomial in x is the same as the order of the derivative of y. Nth degree monomial, nth derivative of y. N minus first degree monomial, n minus first derivative of y, and so forth. This is another one of those equations in addition to linear differential equations with constant coefficients that we're going to learn how to solve. And as is the case with linear differential equations with constant coefficients, when we solve an Euler equation, the first step is to find the complementary solution, the solution of the complementary equation. When we had constant coefficients, our assumption was that the independent solutions were of the form e to the mx. With Euler equations, our assumption is that our independent solutions for the complementary equation are of the form x to some power lambda. That's what we assume. Oh, by the way, this Greek letter here is the Greek letter lambda. X to the lambda is our proposed solution. So this thing here is a lambda. Get familiar with it. If we've had linear algebra, then we've probably seen this Greek letter lambda. We've used it to denote our eigenvalues. So that's our strategy. And this is going to be our strategy whenever we have an Euler equation and we need to find the complementary solution. That we'll assume that our independent solutions are of the form x to the lambda, and we'll compute y prime and y double prime and whatever, and plug them back into the complementary equation and solve for lambda. We'll plug those into our complementary equation. And we'll solve for lambda. So let's see, we have x squared times y double prime, which is this thing, minus x times y prime, which is lambda x to the lambda minus 1, minus, 3y, which is x to the lambda, what do we get? Well, notice something. We have x to a power, and we have x to another power, and we're multiplying them together. So the exponents will add 2 plus lambda minus 2. That's just going to give us x to the lambda. So lambda squared minus lambda, x to the lambda. That's what this term turns out to be. We have the same kind of thing going on in this term. We have x to a power, this is x to the first, times x to a power. The exponents add. 1 plus lambda minus 1 gives us x to the lambda. So this term is this term is lambda x to the lambda minus, lambda x to the lambda. X to the first times x to the lambda minus 1, the exponents add, we just get lambda. And here we get minus 3x to the lambda equals 0. We have a common factor here, x to the lambda, x to the lambda, x to the lambda. We can factor that out. And what do we have? Lambda squared, and that's the only lambda squared we have. We have minus lambda minus another lambda is minus 2 lambda. And then we have minus 3. Now we'll assume that x is not 0. And if x is not 0, then x to the lambda is not 0 either. So we can divide both sides of this equation by x to the lambda. And we just get lambda squared minus 2 lambda minus 3 equals 0. And that's lambda plus or minus something, and lambda plus or minus something equals 0. Let's see, does that work? plus lambda minus 3 lambda is minus 2 lambda. It does work. So lambda 1 is negative 1. Lambda sub 2 is positive 3. So C1 x to the lambda 1 is one of our independent solutions. C2 x to the lambda 2 is our other independent solution. And notice something. Our original differential equation was of order 2. The order of the highest derivative was 2. We had y double prime. We had a differential equation of order 2. And it turns out that we have 2 independent solutions. So in general, if we have an Euler equation of degree n, then we expect to get n independent solutions. So there's our complementary solution. Take a look at that for a second. the right-hand side is a polynomial, but we'll use the method of undetermined coefficients. So the right-hand side was a monomial of degree 2. The right-hand side was 3x squared. So now let's call it A. But we'll assume that the particular solution is a monomial of degree 2. Now, if we were doing a linear differential equation with constant coefficients, we'd look at that 3x squared on the right and go, okay, our polynomial is ax squared plus bx plus c. Here we have a polynomial of degree 2 on the right side. As a matter of fact, on the right side of the equation, we just have 3x squared. So we'll assume that our solution looks like something x squared. And again, we'll talk more about this in a minute. So that means y prime of p is 2ax, y double prime p is 2a, and we plug these in. Okay, x squared times y double prime, that's 2a, minus x times y prime is 2ax, and we have minus 3y, y is ax squared, These guys up front cancel each other out. And if we divide both sides by negative 3x squared, we get a equals negative 1. How about that? So that means that y particular is negative x squared, ax squared. And again, to get the general solution, we take the particular and complementary solutions and just add them together. Heavens to Betsy, what was our complementary solution? C1x to the negative 1 plus C2x to the third. Is that right? That is. So here's our general solution. Okay. If f of x is a polynomial, in other words, if the right-hand side of the equation is a polynomial, we'll assume that the particular solution is a polynomial, consisting only of those powers of x that are present in f of x. For example, the right-hand side looks like this. That's the right side of our Euler equation. Our particular solution, we assume, will have terms with powers of x to the 6th, x cubed, and x squared. So let's say ax to the 6th plus bx cubed plus cx squared. So that's the truth about Euler equations, the method of undetermined coefficients, and polynomials. For right now, work through this example, and tomorrow I will have another video to show you. For right now, just work this example. We will expand our repertoire for Euler equations. And with Euler equations, we will have a section about when things go wrong, because things will go wrong, but there will be things that we can do to right them. But one world at a time. Work this out, work through this example again, the complementary solution and the particular solution. And I will see you again tomorrow.